Hello everyone, this is Group 28 doing Blocks of Code version 3 and we are sponsored by the Draco Lab as well as Dr. Weeks. So this is our team. My name is Jordan Merkel. I am computer engineering. We have Destiny Ellenwood, who's also computer engineering, Annesley Kolb, who's electrical engineering, and Camilla Torres, who is electrical engineering.
For team roles, we organized ownership by subsystem so we could work together in parallel and still integrate smoothly. Jordan overall led the software direction, including full stack integration, firmware support, UI UX, and network architecture. Camilla focused on PCB design, power distribution, and board assembly and testing. Annesley also led PCB design and assembly testing, with additional ownership on CAD modeling and mechanical integration. I focused on firmware development, I2C communication, and reliability through hardware and software validation. This role split up helped us reduce bottlenecks and keep responsibilities clear while still collaborating at key interfaces, especially hardware to firmware, firmware to app communication, and final integration testing.
Blocks of Code is a physical coding system designed to teach kids the basics of programming in a hands-on way. Instead of writing code on a computer, users connect magnetic blocks together to create programs. Each block represents a programming concept, and when combined, they produce real-world output like lights and sound. The goal is to make learning how to program simple, interactive, and engaging for beginners.
Many students struggle when first introduced to programming because the feedback is abstract. They write lines of code, but the connection between what happens and what they type can feel disconnected and overwhelming. Traditional coding environments rely heavily on text, which can create frustration, especially for our younger learners or those who may benefit from tactile and visual interaction. Blocks of Code addresses this gap by transforming programming into a physical interactive experience. Instead of typing syntax, students build logic with tangible blocks and receive immediate visual and audio feedback. Our goal is to reduce that initial barrier and make programming concepts more intuitive and engaging.
So to understand how our system functions, let's look at the full end-to-end flow. It starts with the physical world. Users arrange physical blocks to form their logic. While each block is powered independently to ensure stability across the chain, the brain block acts as the conductor for communication and orchestration. Once connected, the brain block performs an I2C bus scan. It identifies each block by reading its unique Who Am I ID and determining its specific physical order in the chain. This physical topology is then translated into a structured program representation that our software can understand. After the topology is set, our event handler builds and runs the actual program logic. At runtime, events and telemetry flow continuously between the individual blocks, the brain, and the companion app. This allows the output blocks to respond in real time, triggering lights, sounds, or other physical feedback, while the app, connected over Wi-Fi, simultaneously receives updates for live validation. This creates a complete closed loop from physical arrangement to digital interpretation and back to physical output. Here's our architecture split into 3 layers. On the left are the child blocks, which act as I2C slaves. These represent commands like if, then, loop, input actions like a button press, and output actions like an LED flash or a note playing. In the center is the brain block. It is the I2C master and system coordinator. Its responsibilities are scanning the bus, managing configuration, and handling TCP communication between itself and the app. On the right is the Flutter companion app running as a TCP server. It receives JSON messages from the brain, parses it, validates the block sequence, and provides real-time UI feedback such as our 3D block visualizer. Here's how we manage our control and data paths. Starting at the top lane, each child block operates as an I2C slave node. The brain block, acting as the I2C master, issues a discovery and read cycle to retrieve each node's WhoAmI ID and current status. This shared I2C bus provides us with both device identity and live input-output telemetry for the entire chain. In the middle lane, the brain block coordinator firmware performs 2 critical tasks. First, it handles topology inference based on the I2C scan results to determine the physical order of the blocks. Second, it manages runtime dispatch via an event handler. A vital part of this middle layer is our serialization protocol. We package the system state, including the type, timestamp, and block configuration, into a newline delimited JSON format. We chose newline framing specifically because TCP is byte stream, not message framed, so this ensures that the application layer can reliably distinguish where one packet ends and the next begins. In the bottom lane, the Flutter app runs a TCP server on a certain port. It receives the stream, parses the JSON objects, and runs a rule validation engine to ensure the logic follows the correct grammar before updating the UI in near real time. To simplify the logic, the purple box is our control path. It flows from physical topology through the role check and the event handler to trigger physical actions like LED animations or music sequences on the block, while the orange box is our data path. This handles the flow of the block state and telemetry from the hardware through the brain and up to the app for real-time visualization and feedback. Here are our validation rules for the block configuration. Rule 1, the brain block is mandatory and must appear at index 0, meaning it must be at the very beginning of the configuration. Rule 2, if statements must follow the valid structure of being an if block, an input block, a then block, and then multiple output blocks, or one, and then an end if to end the sequence. Rule 3, very similar, loops must also be well formed, should be a loop, a number of outputs, and then the end loop block. Rule 4 is that sequences should remain overall isolated if and loop change should not interleave incorrectly. We issue this rule as a warning rather than an error when it happens because while functionality is possible, it might be confusing to the user to build correctly. On the right, we separate outputs into errors and warnings. Errors are hard failures that must be fixed before execution. Warnings are just advisory, as I mentioned before. They indicate risky or unclear structure, but they may still run. This rule engine gives users immediate feedback and prevents invalid programs from reaching execution and opens up for a learning experience.
As a team, our goals for Blocks of Code version 3 build directly on the idea of reimagining the building blocks of programming. On the basic goal side, we want kids to build programs by literally snapping blocks together. That's why we use magnetic contact-based block-to-block communication and low latency I2C at 100 kHz. Our aim is to have at least 15 functional blocks in this version, each with a clear visual indication so the function is obvious on the table, not just on a screen. Our functional goal is that the brain detects connected blocks in milliseconds, builds the topology, and syncs the state to the companion app. The app mirrors actions in real time so learners can see both the physical program and the digital interpretation. Underneath that, the magnetic contact pads carry both data and power, and the low power design is pushing us towards long active runtimes from small batteries. Our stretch goals push the platform forward as a teaching tool, real-time visualization on a PC or tablet, fully 3D printed enclosures that feel like a finished kit, future OLED or e-paper displays on individual blocks, and eventually voice input blocks so kids can experiment with speech as part of their logic. Finally, our success criteria make these goals concrete. The system should validate 5 or more sequence types across configurations with 15 plus blocks. Lights, sound, and UI should give immediate feedback for both valid and invalid sequences, and the app must track the configuration in real time. And we at least need 60 minutes of active battery life with durable, repeatable magnetic connections. For our engineering specifications, we tie the hardware choices directly to measurable targets and how we'll verify them. At the component and block level, we're using an ESP32 Vroom running at 240 MHz with Wi-Fi as the brain. Every block gets a 2.8-inch SPI TFT with touch, and we use that not just as a display, but to host block-specific UIs, for example, numpads for input or note blocks. For feedback, we use a WS2812 addressable strips and 4x4 RGB matrices, plus a 0.3 watt speaker driven by our amplifier. Power comes from a 200 mA Leon pack, and the magnetic contacts have defined retention and contact resistance limits so power and I2C stay solid when blocks move. The highlighted rows are our demonstratable specs. We want topology to sync to the app in under 200 milliseconds, support chains of at least 15 blocks on the I2C bus, and keep end-to-end to button to LED latency under 50 milliseconds. We verify these numbers with a mix of logs, oscilloscope measurements, and I2C decode on the logic analyzer. For our hardware selection, we focused on giving learners clear multisensory feedback while keeping the electronics realistic for an embedded system. On the peripheral side, we standardized with the ESP32 Vroom so our brain can handle Wi-Fi. Every block uses a 2.8-inch SPI TFT touch display. For lighting, we chose a 4x4 WS2812B RGB matrices and the WS2812B strips so we get both grid style and strip style. For audio feedback, we chose the same Sky CUI speaker driven by our LM3D6 amplifier. For the connectors, we compared the 3 options, and we ultimately chose the Mil-Max part because they give us snap alignment, combined power and data on one interface, and gold-plated contacts for long-term reliability.
For our software, we chose GitHub for version control, ESP-IDF for our firmware, and Flutter for our application.
For our software design, we use a 3-layer architecture. The companion app, its role as user interface, it designs programs, sees live states, and it connects via Wi-Fi to the brain block. The brain block is a controller. It finds child blocks over I2C, runs programs, sends commands to the blocks and status to the app. And then child blocks, they're peripherals. They individually execute actions, light, sound, and display, and report identity and status over I2C. For our software block diagram, we structure the system into 3 layers with clear responsibilities. At the top, the companion app is a visualization layer. It listens for the Brain TCP client, receives and parses block config JSON, validates it, and updates the real-time UI with telemetry and state. The app sends heartbeat and acknowledgements only, so it monitors but does not drive execution. In the middle, the brain block firmware is the controller. It initializes, scans the I2C bus, reads whoami registers, builds a device registry, then loops by requesting status from child blocks, generating updated block config JSON, and exchanging new line delimited messages with the app. It also handles app messages like heartbeat and unknown cases. At the bottom, child block firmware runs as I2C slaves. Each block initializes peripherals such as TFT, LEDs, and speaker, exposes identity and status registers, responds to reads, and applies command packets from brain logic. This keeps physical block behavior and app state synchronized in real time.
Now I'm going to explain why we chose the main power management components in our design. First, we use a USB-C PD trigger module based on our USB power delivery. The standard USB port normally provides 5 volts, which is not enough to charge a 2-cell battery that requires up to 8.4 volts. PD trigger communicates with the USB-C power adapter and requests 9 volts instead of the default 5 volts. Next, we chose the TP500 because we are using a 2-cell lithium-ion battery pack. The TP500 limits the charging current, regulates the voltage, and stops charging once the battery is full. This prevents overcharging, overheating, and potential battery damage. Finally, we use an LM voltage regulator to provide a stable output voltage to our components. The LM2576 regulator steps down and stabilizes the battery voltage to ensure reliable system operation. I'm showing the complete power architecture of our system, starting from the USB-C input on the left and moving step by step to the final regulator outputs. We begin with a standard USB-C input, which normally provides 5 volts. This model negotiates with the adapter and requests 9 volts instead of the default 5 volts. The 9-volt output from the PD trigger is then fed into the TP500. This IC is responsible for safety charging to 18650 lithium-ion cells configured in series. This stage ensures battery safety and longevity. Once the battery is charged, its output voltage, which can range from approximately 6 volts to 8.4 volts, is distributed to 2 separate adjustable buck regulators based on the LM2576. The first regulator steps the battery voltage down to 3.3 volts. The second steps the battery voltage down to 5 volts. We presented the complete system architecture of our project and how power flows through the system. Power enters through the USB-C port and goes to our charging module based on the TP500, which safely charges two 18650 lithium-ion batteries connected in series. Once charged, the batteries provide the main power source. Since their voltage varies with charge levels, we use the voltage regulators to supply stable outputs. One regulators provide 5 volts for higher current components like the amplifier, speaker, and addressable LED strip. The second regulators provide 3.3 volts for sensitive components like the microcontroller and the TFT display. At the center of the system is the MCU, which acts as the brain. It runs on 3.3 volts and controls the RGB LED matrix, addressable LEDs, TFT display, and sends audio signals to the amplifier. For audio, the amplifier boosts the MCU signals to drive the speaker. For visuals, the system controls multiple LEDs and the displays to provide feedback in system information. Finally, magnetic polo pins allow connection to additional block PCBs, enabling modular expansion for both power and communication. Overall, the system integrates charging, regulation, processing, audio, and visual outputs into one modular embedded design. Here I'm presented the final PCB schematic of our system, starting from power input and moving through processing and peripherals. Power enters through the USB-C connector and goes to the TP500 charging module, which safely charges our 2-cell lithium battery pack using a constant current, constant voltage method. For safety, we included a protection stage using the MM3220 protection IC and a dual MOSFET. This circuit monitors for overcharge and over-discharge conditions and disconnects the battery if necessary. Since the battery voltage varies, we regulate it before powering the system. A 5-volt regulator supplies higher power components like the LED strip and amplifier, while a 3.3-volt regulator powers the ESP32 and other logic components. Capacitors are placed near the regulators for filtering and stability. At the center is the ESP32 room, which acts as the main controller. It manages the displays, LEDs, audio, output, and communication. We included pull-ups, puts, and enable circuitry, programming header, and status LEDs for debugging. The TFT display connects through SPI. The amplifier receives a DSA signal for the audio output, and pogo pins connector allows modular expansion through shared power and I2C lines. Overall, this PCB integrates charging, protection, regulation, processing, audio-visual output, and modular expansion into one reliable embedded system.
This is our PCB layout for blocks of code. We placed the ESP32 in the center to keep trace lengths short and routing balanced across all peripherals. A keep out area is maintained under the antenna to protect the RF performance. We also have the power circuitry on the bottom left corner to separate higher current paths from sensitive signal traces. We also have high-speed lines like SPI and the LED data lines, which are also kept short and direct, and decoupling capacitors are placed close to each IC for stable operation. This board uses a two-layer design with a solid ground plane to improve signal integrity and reduce noise between subsystems.
We'll explain the voltage regulator section of our design. We are using an adjustable buck regulator based on the LM2576. A buck regulator efficiently steps down voltage with much less power loss than a linear regulator. For the 3.3-volt rail, which powers the microcontroller and logic components, we set the output voltage using a resistor divider with R1 at 1.5 kilo ohms and R4 at 200 ohms. We obtain a stable 3.3 volts. For the 5-volt rail, which powers higher current devices like LED strip and amplifier, we use a different resistor configuration to set the output to 5 volts. In the PCB layout, input and output capacitors are placed close to the regulator, and the switching loop is kept compact to reduce noise and improve efficiency. Overall, these two buck regulators provide a stable 3.3 volt and 5 volt rails from a variable battery source, ensuring reliable system operation. Now I will explain the charging model of our design, which safely charges two cell lithium-ion battery packs. At the center is the TP500, a charger designed for one cell or two cell lithium-ion batteries. Since we're using two 18650 cells in series, the full charge voltage is 8.4. We added input capacitors to stabilize the voltage and reduce noise. Because the TP500 is a switching charger, it uses an inductor and diode to efficiently transfer energy to the battery, reducing heat compared to a linear charger. We also included LED indicators to show charging status. In the PCB layout, high current traces are kept short and wide, and grounded is carefully routed to minimize noise. Overall, this model ensures safe, efficient charging with proper voltage control and clear use of feedback.
For our audio output, we selected a Class D amplifier to efficiently drive the speaker from the ESP32's digital audio output. Class D topology was chosen for its high efficiency and low heat dissipation, which is important in a compact and closed system. The amplifier interfaces directly with the ESP32's DAC signal and operates on the regulated 5-volt rail to provide sufficient output power. This configuration allows us to generate clear tones and feedback sounds while maintaining power efficiency and thermal stability. This exterior enclosure is what we imagine our blocks of code project to look like in the end. This is a compact cube that houses the PCB, battery subsystem, speaker, and display within a self-contained unit. The 4x4 matrix is mounted on the top of the surface for visualization, while the TFT display is positioned on the front face for clear visual feedback and interaction with our users. A rear-mounted USB-C port provides charging access, and a dedicated power switch allows us to turn the system on and off without disconnecting the battery. We also had ventilation perforations, which were incorporated to support thermal dissipation from the amplifier and power circuitry. And here, to show you a better view of what's really going on inside of this cube, we have the PCB, which is mounted along the bottom plane to maintain stability and minimize wire routing complexity. We also have the battery and power components, which are isolated toward the rear of the enclosure to separate higher current paths from sensitive signal lines. We also have the display, which I spoke about earlier on the front panel, and we also have pogo pin connectors, which are aligned for reliable interconnection between blocks. This layout prioritizes serviceability, structured cable routing, and mechanical robustness during repeated classroom use.
For this phase, we decided to go ahead and solder all 30 of our regulators. That's 15 for the 3.3-volt rail and 15 for the 5-volt rail. Wanted to make sure every single unit was solid before moving forward. To verify them, we tested each one using an electronic load and a bench power supply, and also our 18650 batteries. This let us see exactly how they'd handle real world power demands. The good news is that all three regulators worked perfectly. Even under load, they stayed stable and hit their target voltages without any issues. Running this test now give us the green light. Since the LM2576 circuits passed with 100% success, we know our power foundation is reliable and ready for the next step of the build. Now let's look at how the TP500 behaves during our live charging test. When we power the board with 9 volts and no battery connected, the charger is in standby. The blue LED turns on, confirming the chip is powered but no battery is detected, and the current draw is essentially zero. Once we connect the 2-cell battery, the LED switches to red and charging begins. The current immediately rises to our set limit of 1.5 amps, which indicates the constant current stage. We also observe a small voltage drop from 9 volts to about 8.86 volts. This slight drop is normal and caused by the high current through the leads and the switching action of our regulator. Once the battery reaches 8.4 volts, the current decreases, the voltage stabilizes back to 9 volts, and the LED turns blue to indicate charging is complete.
Before integrating the audio subsystem onto the PCB, we validated the speaker and amplifier configuration on a breadboard. The ESP32 output was connected to the amplifier input, and the amplifier was powered from a regulated supply to stimulate final operating conditions. This allowed us to verify signal clarity, volume levels, and proper amplification without distortion. Breadboard testing reduced integration risk by confirming correct gain configuration and its stable operation prior to PCB fabrication.
To test the Wi-Fi connection and integrity of the signal, we ran a stress test sending packets every 10 milliseconds for 1 minute from the app. Each packet had a timestamp, sequence number, and payload to mimic real network conditions. We sent 542 packets and received 665 with no parse errors. The extra packets likely came from buffering or retransmission. Overall, the system handled messages well, even at high rates. Next, we will improve our method to better track unique packets and measure integrity more accurately. Here, we're testing our JSON generation, the parsing, the visualization, and also the validation checker. In the first state, we have a valid chain and the visualization renders correctly and gives no errors. Then we remove one block to intentionally break sequence integrity. The app immediately flags the issue with a clear validation error, identifying where the structure fails. This confirms that our parser, rule engine, and UI feedback loop are working together as intended. So this test proves we can detect malformed programs in real time and guide users to corrective action quickly.
For our performance evaluation, we organized results by hardware, firmware, and companion app to show end-to-end progress. On the hardware side, power rails were validated under both bench supply and 18650 battery input, and charging path behavior was stable in both charge and discharge scenarios. We also verified speaker and amplifier integration with successful audio output and completed peripheral bring-up for the TFT UI, addressable LEDs, and 4x4 LED matrices. On the firmware side, I2C communication is working across the brain as master and child blocks as slaves. WhoAmI-based identification and registry config updates are validated, command handling paths for display, LED, and audio actions are functioning, and JSON configuration generation from firmware is syncing correctly with the app. On the companion app side, TCP communication with the brain was successful, JSON parsing and validation were verified end-to-end, and UI updates reflect live configuration and status. We also completed a 1-minute stress test at a fixed packet rate with 0 reported errors. These are some of our main difficulties, problems, and proposed solutions we had during development. For PCB interconnection, we had issues with serial port recognition and reliable board communication. So our solution was to replace the MCU path we were using and standardize the connection setup. For the block enclosure, we ran into layout and footprint constraints, so we reprinted a modified enclosure and reevaluated the fit, then updated documentation for the new design. For the custom TFT UI, the challenge was latency and managing multiple UI features at once. Our solution was to build a modular LVGL UI pipeline and optimize task timing and priorities so we can keep real-time behavior. And for the app visualizer, model behavior wasn't ideal at first, so our proposed solution is to continue improving our Flutter 3D animation workflow. Overall, these are our main issues, and this is how we're addressing each one as we move forward.
The total prototype cost came out to be around $824, which is safely under our $1,000 approved budget. This covers all of our core system components, including the MCU, display, audio, lighting, and power subsystem. The primary cost driver is the rechargeable battery and charging circuitry, which supports reusability and safe operation. We maintained the remaining budget for enclosure materials and backup components during final integration. This is our manufacturer level projection, which estimates scaling the system to about 15 to 30 units. This reflects component and quantity increases and bulk hardware requirements. While this cost is higher at small production volumes, optimization and supplier negotiation would reduce our per unit cost in larger scale deployment.
Here's our current status and completion plan. So far, firmware peripherals are implemented and end-to-end communication between child blocks, brain block, and app are operational. Who am I identification and real-time 3D visualization are integrated, PCB acquisition and assembly are underway, and initial 3D enclosure iterations are complete. Looking ahead, our early March milestone is a midterm demo with 3-block configuration and live visualization. After that, we'll finish firmware build-out for each block type, finalize enclosure design, complete PCB assembly, run user testing, and prepare the final demo and presentation. In short, foundational architecture is complete and upcoming work is focused on hardening, packaging, and demonstration readiness. Thank you for watching our critical design review, and we look forward to your questions.